All right, let's dive into one of the most extreme, most mind-bending events in the entire cosmos: gravitational collapse. We're going to watch the final, violent moments of the universe's biggest stars as they give birth to something else, something truly extraordinary.
So this is the big question, right? It sounds like something straight out of a movie, but how does a giant ball of gas become a literal portal to infinity? Well, the answer is hiding in plain sight, inside a titanic struggle that's raging at the heart of every single star. And we're about to unpack the incredible physics that turns a dying sun into a true point of no return. You have to picture a star's entire life. We're talking billions of years, as this perfectly balanced high-stakes tug-of-war. It's a constant battle between two of the most fundamental forces in nature.
So on one side you have gravity. It's relentless, and it's always trying to crush the star down into the smallest possible point. But fighting back with everything it's got is the explosive energy from nuclear fusion happening in the star's core. That's the outward push. For most of a star's life, these two forces are in a perfect dead heat, a perfect standoff, and that's what keeps the star stable and shining. Think of this chart as the star's personal energy menu. It gets its power by smashing lighter elements together to make heavier ones, fusing hydrogen into helium, helium into carbon. Each step up this curve releases a burst of energy, and that energy is what's holding gravity back. But, and this is the crucial part, notice how the curve doesn't go up forever, it peaks.
And sitting right at the top of that peak is iron. Here's the problem. Trying to fuse iron doesn't release energy, it actually costs energy. So once a massive star's core starts to fill up with this stuff, the source material calls it nuclear ash, its engine just shuts down. The outward push from fusion is gone, and gravity's inward crush is now completely, totally unopposed.
And this, right here, is where it all goes sideways, fast. With its fuel tank on empty, the star can't support its own colossal weight anymore. The cosmic tug-of-war is over. Gravity wins, and it wins big. The collapse that follows is catastrophic and happens in the blink of an eye.
Now, not every star gets the black hole treatment. For smaller stars, like our Sun, the collapse is eventually stopped by something called electron pressure. You can only squeeze electrons so close together before they push back, and that creates a white dwarf. If the star is a bit bigger, gravity is strong enough to crush those electrons into protons, making a core of pure neutrons. The pressure from those neutrons stops the collapse, and you get a neutron star. But for the biggest of the big, even that's not enough. Gravity just keeps on crushing. Nothing can stop it.
When that collapse is unstoppable, all the star's mass gets squeezed into a point of infinite density, what we call a singularity. And surrounding this bizarre point is a boundary, a one-way door in space-time itself, known as the event horizon.
Now, it's super important to realize the event horizon isn't a physical surface you could bump into. It's a location in space. It's the exact point where gravity becomes so ridiculously strong that to get away, you'd have to travel faster than light. And since nothing can do that, well, you see the problem. Anything that crosses it, even a beam of light, is never coming back out. Its size is actually defined by a really simple formula. The radius is just 2 times the mass.
Okay, to really get a grip on this, we need to look at these weird-looking diagrams. Those cones are called light cones. You can think of them as your cone of possible futures. At any given moment, you can only travel to places that are inside your future light cone. The edges of the cone are the absolute speed limit, the path light itself would take.
And here's where your brain might start to hurt a little. This is what happens inside a black hole. When you cross the event horizon, space-time itself gets warped so severely that the light cones literally tip over. Look at that. Now, every single possible future path, even for light, points in just one direction, inward, toward the singularity. Escape isn't just hard, it's physically impossible. You'd have to travel backwards in time to get out.
So, this warping of space-time leads to some seriously strange consequences. And to understand them, let's imagine we have 2 different people watching this whole star collapse unfold. One is watching from a nice, safe distance, and the other is, shall we say, a bit less fortunate.
So let's start with us, the safe observers, watching through our telescopes. What do we actually see as the star collapses and forms a black hole? Well, it is definitely not what you might expect.
You know how Einstein's theory of relativity tells us that intense gravity actually slows down time? This is it in action.
From our distant point of view, as the surface of the star gets closer and closer to that event horizon, the light coming from it gets stretched out to longer and longer wavelengths. It gets redder and redder. We call it gravitational redshift. And time on the star's surface appears to slow down until it just freezes. The star seems to be forever stuck on the edge, fading away into nothing.
Okay, but what about the person who's actually falling in? Their experience is totally different. For them, time doesn't freeze at all, not even for a second. For our falling observer, there's no dramatic pause at the horizon. They sail right across it in what feels like a perfectly normal, and probably very short, amount of time. You can see their path on this diagram, their world line. It just continues right on through until it hits the singularity at the center. For them, the end is swift, and it is absolutely unavoidable.
So we have this really strange situation. One single event, but two completely different stories about what happened. To resolve this paradox and see the whole picture, physicists realized they needed a new kind of map, a map that could handle the truly bizarre geometry of a black hole without, well, breaking down.
See, the problem is with the map we were using. Our standard coordinate system. You can think of it as our normal GPS for space-time. It basically just glitches out right at the event horizon. That glitch is what creates the illusion of time freezing. To see what's really going on, we need a much more powerful mapping system, something called Kruskal-Sakaris coordinates. And here it is. This is the complete map of a simple, non-rotating black hole. I know, it looks strange, but this is what physicists call a maximal extension. It's basically the most complete map you can possibly make, showing every single region of spacetime that the math allows for, even places our old map couldn't see.
So let's take a quick tour. Region I, that's our universe, the outside world. Region 2 is the interior of the black hole, leading to that unavoidable singularity. But then the math reveals two other, much weirder regions. Region 3 seems to be a whole separate parallel universe, just like ours. And Region 4 is something called a white hole, the exact time-reversed opposite of a black hole, a place where things can only come out, never go in.
Now, let's put our two observers back on this new complete map. The distant observer just cruises along happily over here in Region I, watching the star's light fade away. But our poor falling observer, their path takes them straight from Region I, across the horizon, and deep into Region 2, where they hit the singularity. This map perfectly shows how both of their stories can be true, all from their own unique perspectives.
So, this incredible map, it solves the paradox of our two observers, but it leaves us with an even deeper mystery. While the mathematics clearly shows these other regions, the white hole, the parallel universe, most physicists believe they're completely inaccessible to us. So it begs the question, if this is the true map of reality, are there destinations we just can't get to? And what else might be hiding in the bizarre geometry of spacetime, just waiting to be discovered?